Welcome to one of the 3 lessons in this class that makes it a business calculus class as opposed to just a normal calculus class. So, in this video, we're going to be talking about applications of the definite integral to business and economics. We've spent kind of all of chapter 6 so far building up to having a mastery of the definite integral and all of its kind of theoretical usages. Let's see how all of that theory we've developed now can be used in the real world. So, let's do, for our first example, let's talk about consumer and producer surpluses and how those relate to definite integrals. If we let P equal d of x be the demand function for a good, what does d of x do? Well, it relates demand for the good to unit price. More specifically, it relates unit price P to quantity demanded. Alright, so this is just a general demand function. Let's say we have some more specific information. Let's say that the market price has been fixed at some value P bar. Maybe it's equilibrium price P bar, that would be a common one. Or maybe there's a law saying the price is this much and then it's the bricks. So suppose the unit market price is fixed at a value P bar corresponding to a demand X bar. So if we were to draw this on a graph, demand curves look roughly like this. Let's say price gets fixed here at P bar, and that corresponds to some quantity demanded X bar. Alright, so this is essentially saying, hey, here's the current state of the market. But based off of our demand curve, what do we see? Well, here's the current state of the market. And there's some people that aren't willing to pay if the price gets any higher than this. But there's some consumers that would have lived up here, right? There's still some quantity demanded when the price is higher. So consumers that would have corresponded to this region of the graph are essentially saving, quote unquote, some amount of money because they would have bought the product anyways, but they're buying it for less than they would have bought it for. It's like when I go to the grocery store and buy a carton of goldfish. I'm going to buy it no matter what it costs. But you know I have my Ralph's card ready to give me that dollar savings. Alright, so how do we quantize that? The difference between what consumers would pay for X bar units of the commodity and what they actually pay is called the consumer's surplus. Alright, so basically what's going on is consumers that would have lived in this region of the graph would have been willing to pay even more money than they actually had to end up paying to get this much of the good. So we call this quantity here, this area, the consumer surplus. So your book does some work with Riemann sums to essentially make this completely formal, completely rigorous. That's on page 467 for the paper version and page 481 for the online version. But really what you need to know is that the formula for the consumer's surplus is the integral from 0 to x bar of d of x dx. So we integrate the demand function from 0 to x bar, and then we subtract away, so that would give us the area under the curve between here and here, and then we subtract away this little rectangle here, which has area p bar x bar. You could have also used our techniques for finding area between two curves from the previous video to write this as the integral from 0 to x bar of d of x minus p bar. Yes, since we're essentially finding the area between the curves y equals d of x and y is equal to p bar, and d of x is higher than p bar on that interval. Alright, so this is our formula for consumer surplus, and again, that's measuring how much essentially saving a consumer is doing, or all the consumers are doing collectively. But anytime you talk about demand curves, you can talk about the dual notion of a supply curve. So if we try the exact same piece of work over in the supply world, say the product has a supply curve capital S of x. And again, that'll be equal to P, because it's going to relate unit price and quantity supplied, the amount that suppliers are putting out into the market when the price is this much. So, if we have, again, a fixed market unit price, P bar corresponding to a unit supply, or sorry, corresponding to a supply quantity of X bar units, suppliers would have been willing to sell at lower prices, and they can gain from the price being here. So this was a demand curve. Now let's swap over to a supply curve. And supply curves look something like that. Maybe the price was fixed here at P bar, and that corresponds to this X bar right here. You have sellers that live over in this region here, where they still would be willing to sell this much, even if the price was lower. So they're essentially gaining money, because they're saying, well, I need to sell this product, and I'm going to sell it at whatever price I can get for it. But the price is already higher than, like, bare minimum. So great, like, we actually have profit there freely. So basically people in this area are gaining money. And so we call this the producer's surplus. Just like how we have the consumer surplus measuring, okay, how much do all consumers who would have purchased at higher prices save? The producer's surplus measures, okay, how much do all suppliers who would have sold at lower prices essentially profit? So, formally, let's make that definition. The difference between what suppliers actually receive and what they would be willing to receive. Think of, for instance, I don't know if any of you are hagglers, but let's say the seller would have been willing to haggle and you just didn't. They've made money off you, essentially. What they would be willing to receive. Alright, so that delta is called the producer's surplus. And we can use the same area between two curves techniques to measure this. Alternatively, you could do it with Riemann sums. We're trying to say, oh, it's area of this rectangle minus the area under this curve, which is given by the formula area of the rectangle, x bar times p bar, base times height, minus the area under that curve, which is the integral from 0 to x bar of our supply curve, s of x dx. We've also written this as the integral from 0 to x bar of p bar minus s of x dx. Same idea. Alright, so those are the definitions of consumer surplus and producer surplus. How do we actually work with them? Let's do an example. Alright, say a given product has demand function P equals d of x equal to negative 0.002x squared plus 500, and supply function I guess I'll just put that on a new line. P is equal to 0.0012x squared plus 0.04x plus 200, where in both equations, P is unit price in dollars, and X stands for quantity. With the first equation, it's quantity demanded. With the second equation, it's quantity supplied. And we'll say x is measured in units of 1,000. Our goal is going to be to determine the consumer surplus and the producer surplus at a certain point. At the point when the market price is set at equilibrium. Alright, for those of you who don't remember your economics classes, equilibrium market price is if you have the demand curve, which in this case would look something like this, and the supply curve, which looks something like that, on the same graph, then the equilibrium price is the price that comes at their intersection, where basically the amount that people are willing to buy and the amount that people are willing to sell is the same. So this is our P bar, and this is our X bar. This is D of X, and this, or sorry, that's S of X. And then this is D of X. And you could put more numbers on that graph and everything like that if you wanted, just to get a better idea of where everything is. But the question is, we need to find the consumer surplus and the producer surplus, which on this graph, just like the pictures we had previously, we'd see that the consumer surplus is everything up there, and the producer surplus is everything down here, where we're splitting at that equilibrium price line, since that's what we've fixed the market price as. Alright, so how do we find that? Well, what we're going to have to do is we're going to have to figure out what P bar is. Like, once we have P bar and X bar, we can just plug into our formulas, but how do we find P bar and X bar? Well, this is a point where the two curves intersect, meaning it's an X coordinate where the Y coordinates are equal. So what we can do is we can set these two equations equal to each other, solve for X bar, and then that'll give us P bar. Alright, so to find X bar, we solve D of X equal to S of X. Now, no, the only reason we solve this equation when we're finding X bar is because we've said X bar is equilibrium. Or, sorry, because P bar is equilibrium. If P bar was told, let's say you were told P bar was set like down here-ish, then X bar would be completely different, but you would have been handed your P bar, so you could have back solved for X bar. Alright, in this case, let's solve D of X is equal to S of X to get that equilibrium market state. So we have negative 0.002 x squared plus 500 D of X is equal to 0.0012 x squared plus 0.04 x plus 200. I'm just going to move everything over to this side, or how about over to that side, get it all out of the way, and you'd end up with 0 is equal to 0.0032 x squared plus 0.04x minus 300. Nice, a quadratic equation. We know we can always solve this with the quadratic formula. Just to make our lives a little bit simpler first, let's divide everything by this leading coefficient of 0.0032. So I'm going to divide that, that, and that. And if you do so, you'll end up with 0 is equal to x squared plus 12.5x minus 93,750. And if you apply the quadratic formula, or you could try to factor it, by all means go ahead and do it. You might multiply everything by 2 then to get rid of this, just to make factoring easier if you want to just brute force it. Anyways, I like the quadratic formula here. It'll tell you that the solutions to this are at x is equal to negative 12.5 plus or minus the square root of 12.5 squared minus 4 times 1 times negative 93,750, all divided by 2 times 1. Run that through your calculator, do some work. That ends up being, this ends up being actually pretty close to a perfect square. Negative 12.5 plus or minus this 612.5 divided by 2, which if you take the positive option, you'll end up with 600 divided by 2. And if you took the negative option, you'd have negative 625 divided by 2. Okay, so we have 2 possible options for x to satisfy this, but it doesn't make sense to have a negative quantity demanded, so x bar is equal to 300, right? This doesn't make sense because it's not in our domain. This one does, so we only have one remaining valid option. That must be our x bar. Alright, so once we have x bar, how do we find p bar? Well, we plug back into either d of x or s of x. Either will work, because this point is on both graphs. So, without loss of generality, p bar is equal to d of x bar, which is negative 0.002 times 300 squared plus 500. And if you run that through, yeah, d of x bar, right? Just x bar is equal to 300. Run that through the calculator, and you'll get 320. Alright, so that's our equilibrium market state. Is 300, and remember, x is measured in units of 1,000, so we really have 300,000 units demanded. At a unit price of $320. Alright, so from here we can directly find the consumer surplus and the producer surplus just by our formulas for each. The consumer surplus is the integral from 0 to 300 of negative 0.002 x squared, excuse me, plus 500 dx minus 320 p bar times 300 x bar. Alright? Run that integration process, you should end up with negative 0.002 x cubed divided by 3 plus 500x evaluated from 0 to 300. You could split that all up as you saw fit. Minus 96,000. And then minus 96,000 is just 300 times 320. So make sure when you do that definite integration, you should get this. You might have that from 0 to 300 and that from 0 to 300. Same thing. By the sum rule. And if you do all that math out, it ends up being 36,000. Let's find the producer surplus. And I'll say what units and everything that's in just a second. Producer surplus is now the integral, is now equal to 320 times 300 minus the integral from 0 to 300, right, 0 to x bar, of the supply curve, which is 0.0012 x squared plus 0.04 x plus 200 dx, which is equal to, do the workout, you'll end up with 96,000 minus what? Well, it'd be 0.0004 x cubed plus 0.02 x squared plus 200x, going from 0 to 300. Run that through a calculator, and you'd end up with 11,700. All right, so these are the consumer and producer surpluses, but there's one quick thing. These are in terms of our x, right? They come from x. But x is measured in units of 1,000. So really, we're not just using 300, we're using 300,000. So to find the actual monetary value, we just multiply by 1,000. So the C at consumer surplus would be $36 million, and the producer surplus would be $11,700,000. And you can think of it this way: if 36,000 is this area and 11,700 is this area, where the x is measured in thousands, if we want x to be measured in ones, aka dollars, right, we would stretch out by a factor of 1,000. So that's where that multiplication by 1,000 factor is coming from. All right, it looks like I actually have office hours in like 5 minutes. So I'm going to actually cut this video here, and then we'll pick up with more definite integral economic stuff in the next one. See you guys there.